We use our hands every day without a second thought. They're astonishingly versatile, able to pick up a fragile egg, twist a screw, or tie a knot with delicate precision. Yet behind these simple acts lies one of the greatest challenges in robotics and artificial intelligence. Teaching a robot to use a hand like ours has baffled engineers for decades. At first, the problem seems easy enough. Build a hand with joints and motors, give it sensors, and program it to grab things. But what looks simple on paper turns into a symphony of complexity in reality. The human hand has 27 degrees of freedom. Each finger can bend, twist, and coordinate with the rest in ways that even the most advanced robotic systems struggle to mimic. Think about what happens when you reach for a cup. Your eyes gauge its position. Your brain estimates its weight and slipperiness. Muscles adjust tension in real time. Tiny sensors in your skin send back feedback about pressure and temperature. All of this happens in fractions of a second, thousands of adjustments before the cup even reaches your lips. For a robot, that sequence must be modeled, computed, and executed perfectly every single time. That's where the real challenge begins. Robots don't have millions of touch receptors like we do. They rely on a few pressure or proximity sensors that offer only a rough picture of the world. And while our nervous system runs in parallel, processing vision, balance, and touch simultaneously, a robot must calculate each movement step by step, often with delays that throw everything off. One small lag or miscalculation, and the robot either drops the object or crushes it. Vision adds another layer of difficulty. Recognizing an object's shape, orientation, and surface properties in real time is a huge computational task. Even state-of-the-art computer vision systems can struggle to distinguish between a smooth ball and a shiny apple under the wrong lighting. And then there's learning. Humans spend years developing muscle memory, from the fumbling grip of a toddler to the practiced movements of an adult. Robots don't get that luxury. They must learn entirely from data, simulations, and trial and error. In 2019, researchers at OpenAI made headlines with a system called Dactyl, a robotic hand trained to solve a Rubik's Cube. It didn't learn the way we do. Instead, it spent what would amount to thousands of years in simulated practice, gradually improving through reinforcement learning until it could twist the cube in the real world. Other teams have taken different approaches. The Shadow Robot Company built a highly articulated hand with tendon-like actuators and tactile sensors. NASA developed Robonaut, designed to perform repairs in zero gravity, a place where even simple movements become unpredictable. And companies like Boston Dynamics often avoid the problem altogether, choosing simple two-finger grippers because they're more reliable, even if they're less human-like. Despite all the progress, no robot yet matches the effortless grace of a human hand. But what this problem reveals is something much deeper. It challenges how we think about intelligence itself. For decades, scientists assumed reasoning and logic were the hardest parts of intelligence, while movement and control were basic. Yet it turned out the opposite is true. Computers can outthink us in chess and solve equations instantly, but getting them to turn a doorknob smoothly or catch a falling object remains incredibly difficult. This realization gave rise to a powerful idea called embodied cognition, the notion that true intelligence doesn't live only in the brain, or in code, but in the way a body interacts with the physical world. Our minds and hands evolved together. The way we manipulate the world with our fingers shapes how we think about it. When we build robots that can touch, feel, and adapt, we're not just programming movement. We're exploring the physical roots of thought itself. The frontier today lies at the intersection of artificial intelligence, material science, and biology. Engineers are experimenting with soft robotics, using flexible materials that bend and deform like muscles instead of relying on rigid metal joints. Machine learning models run countless virtual simulations, teaching robotic hands to grasp, twist, and balance before ever touching a real object. These advances don't just serve robots, they're revolutionizing prosthetic limbs, surgical devices, and even teleoperated systems for space exploration. As we push forward, we begin to realize that the robot hand problem is really a mirror reflecting our own nature. To create machines that move as we do, we must first understand the deep connection between perception, motion, and cognition. Intelligence is not only about solving puzzles or following logic, it's about responding fluidly to a dynamic world. Someday, a robot hand may reach the point where it can match ours, not just in strength or precision, but in intuition, in adaptability, in grace. When that day comes, it won't simply be another technological milestone. It will signal a new kind of understanding, one where artificial minds don't just think, but truly feel the world they inhabit. So when you hear about the robot hand problem, remember it isn't just about fingers and torque. It's about turning contact from a source of chaos into a source of information. It's about seeing with your skin when your eyes are blocked. It's about planning not just where to go, but how to interact through the path, when to stick, when to slide, when to pivot, when to let gravity help. And above all, it's about bridging the last inch between intention and action. Humans were created with this ability. Our robots are learning it now, one careful grasp, one tiny slip, and one successful adjustment at a time.